So now, like I promised for the rest of the day, I'm going to be kind of trying to teach you some practical skills since people in the poll requested that I do some basic R lesson for you. So the one that I decided to do is going to be R for SAS users. Again, many of you might not know SAS, but the only reason it's called that is because I have put side by side R and SAS code for everything that we're going to do, just in case you're familiar with SAS. You'll have some point of reference, but it's fine if you don't know SAS. You can just ignore all that and just learn the R code. So again, we have if you go to this SEA stats page, what we're going to do before lunch here is lesson 1, basic R for SAS users. Now I have everything in, all the stuff that's on here I have in text form. So there's the full text version of the lesson, and if you want to go through it on your own and read everything. And then I've also got these slides I'm going to be presenting off of. So let's get started. And if you have a question about the content, or if you need technical help with anything, I'll help. And we'll talk about getting R going on your machine in just a minute, but I'll start with the intro first. Again, as I said, it's not just for SAS users, but it's, usually I give these classes to scientists who have already been working like as applied scientists for a while and probably know a little bit about statistics. But I think you may also get something out of it, even if you don't have a strong background in statistics. Thank you. And I'll start. I always like to start by saying what we're going to try to have you learn by the end of all this. And we're going to talk about what SAS and R can both do and what the difference is between them. I'd like to think of all these things as tools, different tools for the job. So the more tools you know how to use, the better, right? So it's not like you had to pick one or the other 100% of the time. And we'll talk about some R packages and what they are. And we're going to be using some of the packages, what's called tidyverse, which is a sort of data manipulation package that we'll be using for the first lesson. And if you know SAS, you'll appreciate maybe I'll tell you, because SAS, everything is classified in procedures. I'll say which procedures go along with which R packages and R functions. And the other way that I'm structuring all this is, at least after we do some of the basics, everything should be, in our science field, you start with some data and you want to do different things to that, and as a result have some kind of document that you're going to put out there, whether it's a figure or a writing in a journal article or whatever. So we're going to see how you get from the data, from a file of data on it to the end product. We're going to go through all the steps to get to that importing it into the software, doing any cleaning or manipulating of the data that you need, summary statistics, look at the data by plotting it, fit some models to it, and present the results in graphs and tables. That's what we're going to do in this first lesson with some very simple data. And the way this all works, I showed you already where to look at you can get these slides that I'm presenting off now, and you can also get the full text version, which has a little more explanation if you need to go over it after. And there's also a worksheet. I call it a worksheet, but it's basically an R script with some blanks missing in it, because what I have found is if you give everyone all the code and just say, click run on this, you don't learn, because it could be doing anything you don't know. And if I give you a blank screen and say, type in this code exactly like that, you're probably going to make a typo because it's a lot to type in. And if one typo happens, it doesn't work. So you fall behind. So the compromise is it's mostly filled in for you with a few blanks. I put 3 dots every time, and you'll get that and then fill in the rest. But I just want to point out, if you get stuck filling in the blanks, all the code I've given you, it's all in this text version of the lesson. Any code is given in full without blanks, and as well as here's the worksheet with blanks in it. And I've also given, if you really want like look at the answer key, I've given you it with the blanks filled in too. You can get them both. And now in terms of just logistics, if you have R and or RStudio installed on your own machine, you may use that for these lessons, and that's fine. But all of you should have gotten an invitation to join the Posit Cloud demo server and just make an account on there, which will give you access to a server where I have made an RStudio that can run in your browser with everything already installed on it, and all the example data and all the worksheets are already in it. So that's kind of the most convenient for today. Obviously, it's only for demo purposes. You can't go back into that browser and use your own, analyze your own data on there. If you're going to have to install R on your own later if you want to do that. But just for today, feel free to use that. And when you do go in there, many of you have already done this. But yeah, so once you won't see all these other ones, but you'll see if you go to the Posit Cloud and log in, you'll select this Florence December 24, space it's called, and then you're going to go in there and create new RStudio project. So most of you have already done this, but if you haven't done it yet, now is a good time. And I'll just name the project if you want.
How do you get the Posit Cloud?
So did you get the emails about this? You need to have a sign up link in an email that should then they'll allow you to create an account. If somebody if somebody could forward him that would be great. But you should have it. And then yeah, so you go to that link and it prompts you to create an account. So yeah, this is what you should see if you you should see about the same thing as this when you log in, and you can see there's the example data is already there and the worksheets are there too. But if you're doing this on your own machine, you're going to have to download the worksheet from the website and open it up in RStudio. But if you do it on Posit Cloud, it's already there. Anybody need help with the technical side of it right now? Okay, awesome. So while you can feel free to keep messing with that, but I'll give a little bit more background before we actually start doing some code. Now, R and SAS have a different history, right? SAS is quite a bit older. It started out in the late 60s. SAS actually stands for Statistical Analysis System, and it was made originally by some professors, actually ag researchers at North Carolina State University at that time, and then it kind of got spun off as an independent business, and now it's bringing a lot of money to the Raleigh area, and it's still going strong. And you can see they even had enough dough to throw some back to their original benefactors, and the stats department at NC State is called SAS Hall is their building. So they've done well for themselves over the years. There's no R Hall, obviously, but it's the open source software, but maybe someday, right? But we're talking about R today. It's got pros and cons. So just to go over some of them, well, you can call these pros or cons depending on your mindset. Basically, it's a free software, right? SAS has a very expensive license. R is free and it's open source. You cannot see the code of SAS's statistical algorithms. It is not available to look at. But in R, you could look at any code that is part of it and verify what statistical algorithm is doing by looking at the code. This is either good or bad. Anyone can contribute a package to R. A package is a set of functions, some code, a piece of software that serves a purpose. and it's part of the library of code that makes up the R language. And there is some minimal checking to make sure that there's no like errors in the code, but there's no one. So yeah, this is the pro and con. Anybody can contribute, which is great because it makes a thriving community of scientists that are helping make code, but there's no one top down verifying that the statistical algorithm in that package is correct, right? Versus SAS pays statisticians to verify the statistical algorithms are correct. But it's like the Wikipedia model, right? Like when something first comes up on Wikipedia, it might have some errors, but due to sort of crowdsourcing, essentially, over time, the quality of information on Wikipedia has gotten better. And the same has happened with our code as well, I think. But the cool thing about anybody contribute a package is it means there's like all different people from different applied fields have contributed. And so there's all these specialized things that you can do with R. Like you could use R for all your GIS analysis, basically. You can do it all within R, geospatial stuff. There's a lot of R packages for high performance computing, running things on computing servers. There's a lot of machine learning packages in R, where SAS does eventually get those things, but it's much slower because it has to go through a much longer process to actually make it into the SAS software. And yeah, so the other good thing about R is that there's a lot of different user communities, not just, there's a lot of ag scientists that use R, but there's like social scientists, ecologists, economists, pharmacology, linguists even are using it for their data analysis, and they all have kind of like communities, and you can ask those experts in their applied field and work with them to like they'll help you with your R code. So that's kind of a cool thing about it, community-based approach. And yeah, there's a lot of R packages out there. I think there's like 5,000 or 6,000 at last count. So these are just some, and then now there's like this sort of tradition that packages make a logo shaped like a hexagon, and then you have, I don't have one with me today, but we made a package at one of my jobs, and we got a little hex sticker made that you can, like, if you're one of the cool kids, you can put on your laptop like a bunch of hexagons. Obviously you can't deface government property, so I can't put it on my government laptop. But yeah, I just mentioned this, but a little bit, but the sort of difference between SAS and R, as I mentioned, SAS has like people on their payroll that verify the code. It's top down and centralized. So usually in SAS, like, there isn't like a bunch of different ways to do a particular statistical model. Like, why would there be, right? They have like, okay, this is how you do a generalized linear model. This is the procedure for it. There's kind of one way to do it. In R, there's like dozens of packages of generalized linear model. All of them are slightly different. Some are better than others. That's both good and bad, because like it's hard for beginners, I think, because in SAS, you sort of like know what to do. In R, no one is really telling you, well, this package is like the right one to use and this one's not. There's a lot of options, and that kind of like throws people off when you're getting started. I think it can be good because it means there's more ways to do something, and you can, if certain way of doing it isn't exactly what you want, that other way probably exists out there. But it can be hard, especially for people that are just getting started. So that's something to keep aware of for sure. Another point I want to make about SAS is it is kind of, in the last few years, it seems like SAS is winding down support for its desktop products that like an individual researcher would use on their own computer. They're moving to all this cloud-based services. They're trying to like be more of like a service provider than necessarily like a lot of tech companies are doing. They're not just selling the software, they're selling like the service with it. I think that's great if you're a big corporation that like wants to buy this cloud-based model. It's not very good for individual academic researchers or people in government that are like doing their own individual research. I think it's a bad sign for the future of like being able to use SAS for research. And so, if you're like an old-time SAS user, I think it's a good idea, or just for that reason alone. And people are also, Python is another option, although I'm not really a Python person. There's a lot of stats packages. You can do similar stuff in Python that you can in R, so that's another option. as I said a minute ago, they're all tools for the job. They have pros and cons. The more tools you know, the better. I think R, if you're just getting started, is better to start with than trying to start with SAS right now if you're starting from scratch. But if you do like SAS a lot, I'm not trying to like, destroy your world and stuff. I just want to expose you to what is out there and what R can do. So I mentioned that was about. Anyone have any questions on that? So let's proceed to actually doing some stuff with R. You've been here for like 2 hours. I haven't actually shown you how to do anything yet. So let's finally do that. So we're going to go through this long pipeline. This is kind of like what you would do with any data you get, right? You have to like make sure it's in a good shape, explore it with graphs and tables, actually fit models to it, check if the model is a good model. Once you know it's good, you can use the model to make predictions, which are then the things you present to the world in a document of some sort. This is the actual code. So the code is like on the slide in its complete form. Then we're going to go in and like fill it in as we go in the worksheet. Now, the packages, whenever you start an R session, for the most part, there are some functions that are in the base R that are already loaded, so to speak, when you first start up your R session. But most of the code you're going to use, especially specialized type of statistical models and that kind of thing, is in packages. And the packages are installed. If you've never used R before, none of these packages will even be installed on your computer. Installing means downloading that code from the website and having it on your computer to use later. I've already done that for the Posit Cloud server, but you'd have to install it. You only have to do that one time, right? That's a one-time step. But every time you start R, you have to load the package. If you want to use those functions, you have to load the package so that it's ready to use. You had to load it just like loading a file in any other type of software. So that's why pretty much every R script I have starts with different library calls. Library is the function that loads a package. It's like making that library of functions available for you to use. So the ones we're going to use today are tidyverse, LME4, and EasyStats. Tidyverse is actually a collection of several packages that load all together. It has different functionality for reading in, importing the data, manipulating it, and also plotting. LME4 is a special modeling package for fitting mixed models, and EasyStats has is actually also a collection of several packages, but it is used for making some of the residual diagnostic plots we're going to look at to make sure our model is good. So once you go into your Posit Cloud, the way you get to the worksheet is by clicking on this worksheet folder. And we're going to do the R for SAS users lesson 1 worksheet is the one we're going to work with now. Is this text big enough for people to see in the back? I don't think I can make it too much bigger because you have to be able to fit all these different panels on the screen. So, yeah. So you can see I've left you. So I think we may also be using the LMER test package. I didn't put that on the slide, but that's also a package for doing of running ANOVAs on a mixed model. Well, I've left you a blank. So what am I going to put in this blank right here? Anyone? Library. Yep. So I'll type library in, and so this is basically, I've opened a script. This is a text file. That's all it is. I've just edited a text file. I haven't actually run any code. This prompt down here is the console. That's where you can run code, individual lines of code, or you can run code off of a script. I always recommend putting your code in a script because then you can save that file and use it again later. The way in RStudio that you run code with a script is you either put your cursor on the line of code that you want to run and hit Control Enter, or on Mac Command Enter. So if I want to load library tidyverse, I'll put my cursor somewhere on that line and hit Control Enter. And some messages pop up, but those are part of the messages that pop up when tidyverse loads. If you want to run multiple lines of code at once, you can highlight all of it and then hit Control Enter. So if I want to load these other packages, I'm just going to highlight all that and hit Control Enter. It's going to load the other 3 packages. So you see that different messages come up. Yep, did I load? Maybe I didn't click on this last line, so I'll just make sure that works. Yep, so it says that some of the packages are out of date, but that's okay. I set up this workspace a few months ago, so maybe some updates got pushed to the packages in the interim, but that shouldn't matter. So the next thing we're going to do, yes. Yep. Are you on the server or your own machine? Okay. Yep. Okay. That's right. So you will have to install all the packages beforehand, and I have the instructions of how to do that. I'll just show real quick. So on the you go to the page for Florence 2024. Yes, so there's a link of how to install all the packages. Okay, so if you, yes, basically you just have to copy this line and copy and paste it into your R console and press enter, and it will, yeah, so you would, this is all the packages we're going to use. Copy and paste this line, and then paste it into the terminal here and hit enter and run it, and that'll install them. It'll take 2 or 3 minutes to install them all. Yep. Yes, but that's why we didn't have to do that if you're on Posit Cloud, because I set this up with everything installed already. Yep. But it's good that you're using your own. That's great. So the next step is, yeah, does anyone else stuck with anything? Are y'all good? You need help?
Yeah, I'm trying to get to that. I got to the fund.
Oh, did you set up the account and everything? Here, I'll help you real quick.
I was going to have a just not making it that next step. Oh, man. I appreciate it. You're in the right place there. Great.
Yes, I put it on a URL. So in the code, you can actually download it from the URL. Yep. Yeah, it's just a CSV file that I put on the GitHub site. So yeah, I put an example data file for the lesson is hosted on GitHub site, the stats page. Normally, you would not do that. You would not like read data from a URL directly into R because it could be a malicious file or something. So, but for this, we're going to do it. But normally, you would be reading it from a location on your hard drive, obviously. But here, we're just going to read it straight in. And just another side point: a lot of people work with Excel, and data is by default saved in the Excel format, which is fine. There are special R packages that can read the XLX file, but I recommend that if you're going to read data into a statistical software, whether it's R or SAS, the best thing to use is CSV format because it is just a plain text format. It doesn't have any formatting in it that will be hard for the stat software to parse. So you want to use CSV because also it doesn't require somebody to have Microsoft Excel on their machine to read. Any machine, any computer can read it. So I would usually try to use CSV. So and just to point out, if you're a SAS person, is anyone here actually a SAS user? Can you raise your hand? So like, yeah, okay. So there's enough people that I would just skip all this stuff. If no one here knew SAS anyway, it would not mean anything. But in SAS, oftentimes people use the data step Some people that are really old school, like copy and paste the data into their code and like read it in that way. Terrible practice. I'd not recommend. But in SAS, you can either use proc import or the data step to read from an external file. So this code. If you really want to, like, you could actually like be running SAS on your computer and like do this side by side if you want. You would use this code to do that, because you can actually read CSVs directly from the web with SAS as well if you use proc import. Okay, so yes, if you are using Posit Cloud, we're going to read the data that's in this folder called data. If you look at the files tab, go out of worksheets, you see there's a folder called data that has all the example data in it. So it's already there. But if you're going to use if you're using your own machine, you're going to use this code, which I put that same file on the website on the GitHub site, so that will work. Now, if some of you have never seen, this will be like the first actual R code that you've seen. So let's go through what each of this is doing before we actually do it. Okay. We're going to be importing a data set from a CSV file, which is basically like a spreadsheet with columns of data in it. We're going to be importing that into an object in R called a data frame. And we're going to use a function called read_CSV to do that. And a function, what is a function? Well, it's some code that takes an input and gives you an output. And the input in this case is the name of the file where the data is, and the output is an object containing that data. So we're importing in the data. And you see there's like this little backwards arrow. That means we're going to take the output of this read CSV function, and we're going to put it in an object called NAS soybeans, because this is data from the National Agricultural Statistics Service soybean yield data from a bunch of years. So that's what we're going to be using as our example data. NAS soybeans is what I called it. And so the syntax is the name of the function, parentheses, the arguments, which are the input to that function. So read CSV, parentheses, the name of the file means take that name of the file, and read CSV means do something to it, read the data in that file, and then we're going to put it in a new variable in our environment called NAS soybeans. Any questions on that? So let's do that and see what happens. So I've left a blank, so we're going to fill in that blank just like it was on the slide. We have to make a backward arrow. That's a less than dash. And you don't have to put spaces around it, but I usually do because it makes the code more readable. The function is called read_CSV. And you can see that some stuff pops up because RStudio is trying to intelligently help you write your code by prompting. When you start typing a function name, it will give you all the functions that start with that. You can hit escape to make that go away. So I've typed all that. I'm going to hit enter. Now, if you're doing this on your own machine, you can see that some lines begin with a pound sign or a hash. That means that's a comment. So it means this is just a comment. It's not actually code that needs to be run. So if you want to run this, if you're running this on your own machine, you just delete the comment, and then you can run that line of code as well, and that'll load the file off of the website where it's at. So you can see once I ran that read CSV, you can see there's an object in our environment. We have a new data object called NAS soybeans. It says it has 2,500 observations of 4 variables. So you can click on this blue triangle. We'll give that a bit more room. And this is just like a helpful way to see what's in there. You can see there's 4 columns of data, each of which has 2,500 rows, the year, the state name, how many acres of soybeans were cultivated that year in that state, and what was the yield, bushels per acre, that year. That's our data that we're going to work with. So far, so good. Has everyone got that? Is anybody not able to get the data loaded? I see. Yes, if you didn't load the tidyverse library, yes, then you would have to do that. You have to load tidyverse. This read on CSV is like an optimized function for reading in data. The base R has read.csv. Yes. So if you didn't load your packages, you're going to have to load that for later. You will have to do that. So definitely make sure you did that. Now that we have our data in our workspace, we would want to look at the data. Now, yeah, again, in SAS, you can do proc print, and that'll show you the first few rows of the data if you want. Or you can do proc contents to look at the data, what all the columns are named. In R, the functions we're going, there's a few different functions you can use to look at the data. Is anyone stuck? I can, if you're stuck, like I can help you. So just raise your hand if you need help. But helping each other is good too. Yeah, so in R, you can use the function head, which gives you the first however many rows of the data, it will print them. So you can see that this one has, you can see there's two arguments, two inputs to that function. Yes. Okay, let me help you out. That you didn't want to hide your like your hide. Oh no, yeah, there's a slash there. Yep. That slash. Now run it. Now run it. Yes. Now you have to load those packages. There we go. Now go ahead. Anybody else not up to the phone?
I'd be like, look, there it is. But yeah. Oh, right, yeah. Just have to give us some details.
How we doing? Everyone good? Okay, cool. So yes, let's see, where were we? These are just some different ways that you can look at what is in your data. So let's try, and I just also want to point out, this has, the head function has two arguments. The name of the, every time a function has more than one argument, you put commas in between to space them out. So there's, the first argument is the name of the data object, the data frame that we're going to look at. And the next argument is the number of rows we want to print on the screen. Head, NASA soybeans. If you do it without that argument, it will give you a default number. I think it's 6, but we'll do 10. So let's try that. So we're just going to fill in the name of the data frame as the first argument, SAS soybeans. And you can see that if you start typing an object that already exists, it will, if you just hit tab, it'll finish typing it for you. So that can be helpful. Now I'll hit Control Enter. You can see there's the first 10 rows of the data. Another way to just take a look at your data is the summary function. So a data frame has a summary. Yeah, data frame is the name of the type of object that the data are contained in. It's a special type of object for a table of data with columns of all the same length. So if we want to do a summary of the data frame, we type summary parentheses, the name of it, and you can hit Control Enter and run that. And it will give you summary statistics on each column. So for any column that is numeric, it'll tell you the minimum and maximum. We have data from 1924 to 2011, for example. And the column for the state name is not numeric. It's like Alabama and Arkansas and everything like that. So it just tells you its character. For the other ones, it gives you summary stats. Helpful. There's another function in the tidyverse called glimpse, which gives you a compact view of the first few rows of each of the columns in the data. So we'll try that one too, just to show you what it does. So it tells you how many rows and columns, and it tells you the data type. This DBL stands for double, which is double precision, which is like a computer term for a number that might have decimal points in it. So year, acres, and yield are stored as numerical values that can have decimal points, not just integer. And state is CHR for character because it's a text variable. Is everyone able to do that? Have we all been able to get to this point? Okay, great. So now we can hopefully proceed with more efficiency moving forward. Yeah. Now, what we want to do is, let's say we only care about the southeast states for our analysis. Well, if you were a SAS user, if you want to subset a SAS data set, you use the data step to do that. So that's, if you care to look at the SAS code, that's how you would, if you just wanted those 9 states, that's how you get the data in SAS to just a new data set with just the 9 states that we are analyzing. The way you do it in the tidyverse in R, we use a function called which means take a data frame and keep only the rows that meet a certain condition. So what we're going to do is, well, the first thing we're going to do is create a character vector. What is that? Well, it is a list of, a vector is basically a list of data objects or items that all have the same type. And we want a character vector. So these are this NASA soybeans data set has data for all states, but we only want the southeast region, let's say. So we create a vector. This C function, C stands for combine, and it means create a vector with this data in it. So we're going to create a vector called SE states, southeast states, that has the names of the states that we want to use, and they're all in quote marks separated by commas. So in R, you can use either and SAS as well. You can use single or double quotes to set off text variables, as long as you use the same one for the beginning and end. You could use single or double quotes. Here I use single quotes, but you could use double as well. And it means create this and store those names in a vector. And then we're going to say, okay, now we're going to filter our large data set using this vector. And so this in operator means there's a column in the data called state, we want to keep only the rows of the main data set where the state column has a value that's in this short vector of states. So we're only going to keep data from those 9 states, and well, it's get rid of the rest, but we don't actually delete the rest. We just create a new object with a new name that's going to be a smaller subset of our original data, but our original data will still be there under its own name. We're creating a new data frame with less number of rows, only ones that match a condition. So yeah, you do this all the time in any type of data analysis. You probably have rows that you don't want to do your stats on, so this is how you would get rid of them to do that. So and I talked for so long that it went to sleep, so we'll bring that back up. But it should come back to where we were a second ago. Yes, so we have to, first off, use our assignment operator, that backward arrow, to create a new variable. And we're going to use the C function to create a vector. So I've replaced the first blank with this get C and hit Control Enter. Now we have a new variable in our environment, SE states, and you can see it's a character that goes from 1 to 9. So there's 9 states we're going to keep the data from. And this next blank is going to be what? Filter. Yes, we're going to filter this first argument, the data, the large data with 2,500 rows, and we're going to keep only the rows where state is found in. This in you can read as is found in. So basically filter the data, keep only the rows where the state column value is found in this short list of states. So then if we hit Control Enter, you get a new data set, new data frame called SE soybeans, which has only about 700 odd rows. So those are only the data for the Southeast states. Yes, so far so good. What if we wanted to do some computations on our data to create a new column of data? In SAS, you also use the data step for that. So the data in this, there's a column called acres, which is the total number of acres that was planted or was harvested, and the yield is the bushels per acre. So what if we wanted the total number of bushels? Well, we can multiply the bushels per acre times the number of acres to make we're basically doing a computation on some of our columns to create a new column. In SAS, you would do that with the data step. In our tidyverse, we use a function called mutate, which means to do some computations on the data to create a new column. And so, yes, so the first argument is the name of the data. And the second argument is whatever computation we're going to do. And you have to give it a name to say what the name of that new column is going to be. So it's called total underscore yield equals acres times yield. So we're going to take the acres column, multiply it by the yield column to get the total yield. And this time, instead of making a new data frame, I'm actually going to assign the result back to the original data frame, to SE soybeans again. So I'm going to overwrite the data frame with 700 rows and 4 columns with this new data frame, which is 700 rows and 5 columns. It's identical to the one before, except it has a new column on it. So usually when you add a new column, you can just basically overwrite the original data with that new data frame that has the added column on it. So I'm going to do that now. So I'm going to use the mutate function. Oops. Mutate. And we will do acres times yield. Again, you don't have to put spaces between each operator, but I like to because it makes the code easier to read. It would work just as well if you didn't have any spaces in between these equal signs and commas and stuff like that. It would work just as well, but I like the way it looks better with spaces. It just makes the code easier to read if you have a long line of code. So I'll put them back in so people can actually read it. Okay, so hit Control Enter. Now look, so now Southeast soybeans has 5 columns in it, not 4, it wrote over the original one with the new one, and we have a column. If you look at it, you can see it's got total yield in there. Okay. Let me see. What did I say was the time that we're supposed to go to before lunch? 12:30. Okay, well, yeah, let's just I mean, if people need to like go use the bathroom, I guess we'll have to wait 20 minutes. I'll just try to get as much done as possible in 20 minutes, and then we'll take a break. But we're still doing good. Okay, so now another point I want to make is that if you're doing data wrangling like this in SAS, you can actually do them both in the same data step. You could, if you wanted to like make a subset the rows and also make a new column, you can do it in the same data set with SAS. You can also kind of do it all at once with R as well. And the way we do that is with this operator, which will chain different data manipulation operations into one statement. And basically what the pipe does, it's a parenthesis, forward arrow parenthesis, percent, forward arrow percent. What it does is it takes the result of the first line and passes it to the next line as the first argument. So basically what this line of code is doing, or these 3 lines of code, is it's taking the original data, NASS soybeans, it's passing that to the next line. It's saying, take the result of this line up here and filter it. Then do another pipe, take that result and pass it to the mutate function, which will then add a column. So we're just doing what we just did, except all in one step. It's kind of nice for making the code more concise. So that's what I usually like to use. And that's what you'll see if you look at other people's code. A lot of people use this. So it's good for you to know how to use it as well, because it's the most common way, I think, nowadays to do data manipulation in R. So you'll see this if you see anyone's R code. Yes. There's a keyboard shortcut to insert the pipe. What is it? It's like, let me see. You can look at that by looking at the keyboard shortcuts. Let's see, what was it? I don't ever use it. I should though. Well, one thing at a time, right there. Yeah, I'll find it later and we'll play with that. But let's just type it in longhand. So we use percent greater than percent, and that's the pipe. And right, and so the first thing we're going to do is filter, and we're going to pipe that to the next line, and then we're going to mutate as well. So this will just do exactly what we just did again. So it's not doing anything new, but it's doing it in a way that is more commonly done. So this is what you'll see when you see people's R code, and it's more concise. So if I hit Control Enter, nothing happens because I've just made the exact same thing I just did a second ago again. So nothing happens. You also might want to reorganize the data, the order of the rows. In SAS, proc sort is what you use. In R, right now the data is organized by state and then by a year within each state. What if you wanted to do first year then state? Well, you can use the arrange function, which will sort the data. And so the first argument is the name of the data frame, and then the following arguments are what columns you're going to sort on in order of how you want to sort them. So we want to first sort by year, then by state. This is how we would do it. And so, yeah, if you look at it right now, it's like all the Alabama ones are first sorted by year within that. But what if we want to do it by year and then state? We would do arrange first by year, then by state. I hit escape to get rid of that. And then, so yeah, if I hit Control Enter now, yep, so the Southeast soybeans is now, all the 1924 is at the top, sorted by state within that. Okay. And you could even pipe more than two, you could put that filter, mutate, and arrange all into one statement if you wanted to. So we would, yeah, you could filter, you could get rid of, use only the rows that you want, make a new column, and then sort the data all in one statement with pipes. So that's how you do that. But again, this is all the stuff we've already done. Just so I just gave you that whole code. This will do exactly what we just did, just written more concisely. Okay, next step is we might want to reshape the data. So right, this data is long and skinny, right? It's like only 4 columns wide, but it's hundreds of rows long because each row is a unique observation where it has an identifier columns of where that observation came from, the year and the state, and then the data that were collected there, the acres and the yield. And that is usually the format we want for statistical analysis. The long, skinny format, they call it tidy data because each row is a unique observation. But it's not very good for like if you wanted to make a table and put it on a page, you can't have that long, skinny. You want wide format to fit on a journal page, let's say. So what if we wanted to reshape the data to, instead of being long and skinny, to have year and state, and then one data point? What if we wanted like year by state to have a more compact table? We can do that for visualization. How do we do that? So yeah, this is a animation explaining how it is done, right? So this is like wide data, long data, and it'll tell you the R code in each case. Pivot longer takes wide data and makes it longer and skinnier. And pivot, so now you got long data. To make it wider again, you use pivot wider to make it wide again. But we'll go through that in actual a little bit more detail in a second. In SAS, proc transpose is what you use to go from long to wide or wide to long. In R, we are going to go from long to wide this time. So we're going to use pivot wider right now. And the arguments are the names of the columns that are going to be used to as keys to pivot the data. So we now want the ID column to be year. So we want to have a column for year going down, and then the column names from state. So we want one column for each state. So we want each row to be a year and have all the states in that year. And what values do we want to put in that new table? We want to put the total yield in that table. And so that's how we're going to do it. So this says what variable will be going down the rows, what variable will be going across the column names from, and what value of data will be in the table, values from. That's how we do it. Pivot wider. So we want pivot underscore wider, and you see that I'm going to total yield wide is the name of the new data we're going to make, and we're going to use the pipe to say we're going to start with Southeast soybeans, pipe that to the next line, and then we're going to do this operation on it. We're going to pivot it and make a wide table. So years going down the rows, state going across the columns, and total yield is what's in the data. Now I hit Control Enter and run that. Now we have yes, total yield wide is 88 rows by 10 columns, and you can if you type the name of it in the console, you can print the entire thing, or at least whatever fits on the screen. You can see now we have a column for year and a column for each state with the yield data in it. So that's our new table we just made. What if we wanted to go from wide back to long? We can use pivot longer to do that, and we have to. This is how we're going to. So yeah, this will take us back from the wide data to something like the old data we had before. We're going to call it total yield long. We're going to use pivot longer. Now this minus year means pivot everything except for year to its own column. And that column is going to be named state, and the data are going to be back to total yield. And we have to put these in quotes now because they're not columns in that data anymore. We have to specify that name, right? Because there's nothing called state in this data anymore. So we have to tell it, well, putting in quotes to make a new column called state that has that in it. So we're basically just undoing what we just did. Pivot underscore longer. Minus year means all the columns except for year. And names too means the column names will be made into a new column called state. And values too means the data values will be made into a new column called total yield. Hit Control Enter. Now you notice it didn't give us exactly back what we had before. It has more rows now, 792 instead of 767. And that's because there was some missing values in this table. It didn't have every combination of year and state in it to begin with, but when we made that Y table, it had some empty cells in it. So then those got put back in. So that's just something to keep in mind. Whenever you reshape the data, sometimes, like let's say there wasn't data for 1924 for Alabama in the original data set, it would still make that combination because we have 1924 data and we have Alabama data. So it would just put a missing value in that cell. And that's why they are different. Yes, I think we should be able to stay on schedule here. We have the next couple steps in the process is to graph the data. Let's say we have soybean yield over time. We want to see if it changed over time. Well, you can make a time series plot, like a line showing the trend over time in the data. In SAS, you can do that with proc sgplot. How are we going to do it in R? Well, the code of it is a little bit complicated because it uses a package called ggplot2. I don't want this lesson to get bogged down in the details of how to make the plotting code because there's like all different ways you can customize it and that kind of thing. So for that, you'll have to look at my ggplot2 lesson, but I just want to go through the steps that you would go through if you have data. You always want to make a plot of it. So what I've done in this code is first, just to make the plot a little simpler, I've filtered the data down even more to just have 4 states. And so I filtered it for 4 states, and then we're going to plot with the ggplot function. And the main thing you need to keep just to be aware of right now is that in the ggplot function, you have to specify which column in the data is going to which attribute of the plot. So like if we want year to be on the x-axis, we put x equals year. That means it'll go along the x-axis will be year. Yield, the bushels per acre, is what we're going to plot as the y-axis. And color equals state. We're going to make a separate line for each state with a different color. And geom line means what kind of plot are we going to draw? We're going to draw a line plot. And then you can do different things like make the line have different width. You can change the look of the plot with a theme. You can make a label on the x-axis or the y-axis. And you can move where the legend appears on the plot and that kind of thing. Those are all things you can modify. And those are just some of the many things you can modify. But I just wanted to show you that. So yes, the only blanks I've left you is the most important part, which is which columns in the data. Well, the name of the function is ggplot, and which column in the data goes to which thing in the plot. So we want to plot year on the x-axis, yield per acre on the y-axis, and we want to have each state have a different line with its own color. Hit escape, and then if you hit Control Enter, a plot will appear in the plot panel. Oh, I didn't run the line of code. So yes, you see I got an error because I forgot to create the 4 states variable, and then it was trying to look for that variable. ggplot couldn't find it because I didn't define that variable before running the ggplot. So I'm going to make that, run that, and now make the plot. So yeah, you can zoom in on that. yeah, so it's not the world's greatest plot, but it shows a generally increasing trend over time of yield soybean in all these states. Yes. Well, I'm not going to do that one this time, but I mean, it does kind of like get you partway there. It's only 1 hour long, so but yes, it'll get you part of the way there. And definitely with plotting code, right? Because it's not a statistical algorithm. It's perfectly fine to just like go online and copy and paste other people's plotting code and like play with it because you can't really go wrong with it. So yeah. Another one that I also want to show, another type of plot, is you could also make a multi-panel plot with ggplot. Let's say instead of having a line all on top of each other, we wanted a separate panel for each state. You use this facet wrap function to make a separate facet or panel for each state. Wrap meaning it'll go onto multiple rows if there's too many to fit all next to each other. So you can put by this tilde symbol means by state. So you want to, if you run this line or this set of code, yeah, so it's same data, just plotted in a different way with a separate panel for each plot. And I got rid of the color on that one. You could have still had color equals state if you want. Now that's not really necessary, I guess, because they're all in different panels anyway. But you could still have put color equals state in there as well if you wanted colors. Yes, so there's that. Now, yeah, I think let's see. Yeah, we'll go. I don't want to like make people miss lunch, so I'll what we'll do is we'll do a couple more minutes. Then after lunch, we should have time to finish up lesson 1 and do lesson 2. I think we should have plenty of time for that today, and that will be kind of the day's work here. So we're doing decent on time. Well, the next thing I'll just get started on it slightly before we break for lunch is you might want to do summary. Yeah, so we haven't even really done any statistical modeling yet. That's for after lunch. Once you're like full, you don't want to do that on an empty stomach, right? So we'll do that after lunch. But before doing statistical models, you do want to just do summary statistics like the mean and various easier things to just get an idea of the data before we think about modeling it with a formal statistical model. Let's say we wanted to present a table in a paper that had the different soybean yield statistics for 1930, 1940, 1950, every 10th year, just to put it in a table. Well, you could do that in SAS or R, and basically, so what we're doing is breaking up the data into groups, states, and calculating a summary statistic for each group. So the way you do that in R is group by tells which groups to break the data into, and summarize tells what summary statistic to calculate on each group. In SAS, there's different ways to do it. Proc SQL will do that for you, but you just take that for granted. So basically, this is what we're going to calculate here are some summary stats on the data. And we're going to use pipes to do it all in one step. Now, first, we're going to say get every 10th year. So get only years where year is evenly divisible by 10. Year, this means the remainder of when you divide by. So year, anything where the remainder is 0 when you divide by 10, that'll give us every 10th year. Then we're going to group the data by year. Yeah, so this will give us the average across all the states. It'll give us, let's say we wanted to know the total acres of soybean that was harvested across the entire Southeast region in each of those years. We're going to group the data by year and then sum up the data for all the states. This sum function will sum up all the states. And what if we wanted to know the total bushels of soybean that was harvested? We would sum the total yield column. And what if we wanted to know the average yield per acre across those 4 states? Well, the states have different sizes, so we'd want to take a weighted average of the yield weighted by the size of the soybean acreage in each state. That's how we would get the average yield in, let's say, 1930, would be taking the weighted average of the yield rate for each state weighted by the size of the state. And weighted.mean is the function you use for that. And so you can see that, yeah, we've done a filter. Then we're saying take that filtered data, group it by year, and for each group, calculate all these summary statistics. And summarize always can take multiple arguments, multiple summary statistics. It's a list of them, and you put a comma after each one if you're going to do multiple summary statistics. So that's what we're going to do. And so first, we filter, right? Keep only the rows we want. Then group underscore by means you can hit escape to get rid of the automatic help there. Group by year. So do this computation on each year separately. And then summarize means calculate these summary statistics. And grand total of acres is going to be the sum of acres. The grand total of yield is the sum of total yield. And the weighted mean of the yield per acre is weighted mean of yield, comma, acres. So take the yield average by size of the soybeans. Now, you notice I did not tell R to assign this result to any new data frame. If you just run a computation without assigning it to an object, it'll just print the object in the console without writing it to something we can use later. But so if I wanted to do that, I would have to put it here and make a new data object, whatever you want to call it. And, you could put like summary stats and give it a new, make a new variable. But that's how you would do that. But I'm just going to want to print it to the console. We don't really need this for later. So Control Enter. And now there's the summary table. So you've got various summary statistics for the soybean yields for a bunch of years. Yeah, so you can see we have a couple of things left in lesson 1, but I think people are probably tired of doing this now. So let's take a break. Back again from lunch, and well, it was kind of a decent stopping point that we got to back then, because we had got to the point where we loaded in the data and did different things to kind of shape it in the way we wanted. And then we made some graphs, some plots, and we calculated some summary stats. Well, after all that, we never actually got to any statistical models yet, right? I mean, seems like that's kind of where it's at, or that's the bread and butter, but it's, there's a lot of steps you have to go through before you get to that point. But now we've made it that far to our first statistical, we've done some statistics and we've calculated averages and that kind of thing, but what about a statistical model that we can actually use to make predictions? That's where the money's at. So that's what we're going to do next. And so yeah, we finished the summary statistics, and yeah, I'll just skip that point. But we're going to do some statistical models now, and it's a good segue because the future lessons in this curriculum are all about the statistical models. So we're kind of going to take it for granted that the data are in the right shape and that kind of thing. Yes. Okay. So hello, testing. Okay, there we go. Someone else joined the teams there. Okay, so the statistical modeling, obviously SAS and R are statistical modeling software, so that's kind of their main thing. And there are many different options whenever it comes to fitting a statistical model. I can't go into all of them. We're just going to barely get started with it today. If you know SAS, as some of you said you did, this is both good and bad about SAS is the modeling procedure code is really short a lot of times because you basically say, okay, I want to fit this statistical model, and then it automatically spits out like all possible output you could possibly want related to that, like the parameter estimates, mean predictions, variance, covariance matrix, like all that stuff. It just like throws it on the screen for you. You don't have to say, give me the parameter estimates, give me the, matrix or whatever. It gives it all to you. Well, the R code isn't quite like that. Basically, you have to fit the model, and then that goes to an object, and then you have to like go through and say explicitly, now show me each thing one by one. And honestly, that's both good and bad, because sometimes it's nice to not have to like write that, but it's also so that's an advantage of SAS. But for R, it is nice to know exactly what you're looking at each time, and say it one by one. So yeah, well, we want to do just a simple linear regression now. We're going to ignore the different states right now and just do a very simple y by x linear model fit. We want to know, and also, again, it's a linear regression, so it cannot model any nonlinear trend, right? Linear regression, people kind of overlook this sometimes, but it assumes that the relationship between the variables is linear. You multiplying by a slope and adding an intercept. That's all you can do in a linear regression. And that's what we're assuming, not to mention assuming normally distributed error and all that kind of stuff. Well, in SAS, there's a procedure for that. But in R, we're going to use the function called LM, standard linear model. It's kind of the basic function that fits linear models in R. And this is the first time you're going to see a formula notation in R. This is how model formulas are written in R. They are always on the left-hand side is the Y, the response, or the dependent variable is on the left-hand side. Then you have a tilde, squiggly, that's on the upper left corner of your keyboard if you can't find that. And then any predictor variables go on the right-hand side, separated by pluses if you have more than one. But we only have one. We're just going to say, is yield a function of time? The time variable is year in the data set. So just yield by year. Yield is the Y, year is the X. And then you also need to have a data argument to that function. Data equals, which tells which data frame do those variables yield and year. Where should R look for them? It should look for columns in Southeast soybeans called yield and year, and that's where it's going to get the data from. That's how you fit a linear regression in R. So I've given you the blanks to fill in on line 97, although if you modified the code, your line number might be slightly different, but that's where we should be at the moment around. LM is the function, linear model. Left-hand side is the dependent variable, yield. Right-hand side is year. And we want to save the results of this assign it to a variable so we can use it later to look at. So we're going to make a new variable called yield fit, and we're going to put the results of this linear model into that object, which we can later extract different things from and look at and work with. So we hit Control Enter, and now we have yield fit. Well, there are various functions you can run on. So you see nothing happen, right? Like you don't see any output. We don't know what the model ran, but we don't. It fit, but we don't know what the results are. Well, the first one to look at is using the summary function. We can get a printout of a bunch of different output related to the model. It's actually quite a lot. So you can see, yeah, there's quite, I'll make this a bit bigger so we can see what's going on. Well, it gives us the formula back. It gives us some summary statistics on the residuals, which if you know a linear model assumes normally distributed error, you want to be symmetrical distribution of the residuals. So that looks good because they're, the quartile, one is -3, one is +3. It's like, well, that's pretty good residuals. But the thing that people mostly look at are the coefficients, and this is the intercept and the slope estimate, and that's kind of like the main result of the linear regression: the intercept and the slope. So there's an intercept, which in this case doesn't mean a whole lot because it's like the yield if the year was 0, which doesn't really make sense to go back that far. So but the important thing is the year slope is 0.28. So it's a positive number, meaning there's an increasing trend with an additional 0.28 bushels per acre yield on average is how much the yield went up by every year. And you can basically get a test statistic on that showing that it's very, very highly unlikely that you would have observed that high of a slope if the true null hypothesis was that there was no trend. So yeah, if there was no trend, it would be extremely unlikely to see that steep of a slope in your data. That's what the p-value is telling us. And we can also do some other things with the, we can also get an ANOVA table for that, which is just going to have one term in it because we only have one predictor in the model. And because you only have one term, the p-value is the same as the one from the linear model output. So you can put an F statistic on it as well. And this one, check_model, is a nice one to look at, which we probably should have looked at before we looked at the results, because check model is a function from the EasyStats package that looks at the residuals and makes sure that the residuals look the way they should. Does this model meet the assumptions of a linear regression model for it to give a valid answer? If they don't, then we can't use it. So let's take a look. You have to zoom in on this to see it. If you click zoom, it'll pop it open in a new window. And so the basic, it's kind of hard to tell because it's so flattened out here, but these are various diagnostics of the residuals, and a linear model like we're doing assumes normally distributed residuals. If these points are not on a straight line, that shows deviation from normality. So it's almost perfectly straight. So we say, well, they're pretty close to normal. We don't want there to be a increasing trend in the residuals as the fitted value goes up. It's like, well, there's not really one. There's no trend in this line. It's pretty much flat. And maybe you could say the variance is a little bit higher here versus here, which could be a problem, but it's not severe. So we say, well, yeah, because the homogeneity of variance should be flat. Maybe it's going up a tiny bit, but I wouldn't worry about that much deviation. So we say, well, those are good diagnostics. We can say this is a valid model from the perspective of having good residuals, and it means we're meeting the assumptions of a linear regression model. So we can be happy with those diagnostics. That seems a little hand waving, but to be honest with you, people like to use formal tests for normality of residuals and that kind of thing, but I never use them because I think that they are too sensitive, and all linear models doesn't have to be perfect when it comes to meeting the assumptions. It just has to be close enough because, right, a normal distribution is a mathematical equation. There's no data set will follow that perfectly. There's always going to be some deviation from it. So if you have a big enough data set, you'll always get a significant deviation from normality if you test it too strictly. So it just has to be close enough. So if you eyeball it and it looks normal, that's good enough, basically. Just like there's no such thing as a perfect circle in nature, right? A circle is a mathematical equation that humans created because there's things that are pretty close in nature. But since everything is made of atoms, there's no such thing as a perfect circle, right? So there's also no such thing as a perfectly normal data set because they're all made of data not going to be perfect. Just a little philosophy for you there. Yeah, so we've gone through all this. Now, okay, our residual diagnostic plots looked great. All the assumptions were met, right? Not necessarily, because one of the key assumptions of a linear model is that all data points are independent as well. And that is not the case here, because we're not just independently looking at yield, the relationship between yield and year. There's actually, the data come from 9 different states, and the yield value from the same state in different years are not independent. Like maybe the climate is more favorable for soybean production, and so the yield per acre is just higher in one state. So all the data points that are taken from that state will be higher than average, and same if it's a poor one. And so we can't, the residual diagnostic plot is not going to tell you that, right? That's just something you have to know. Like, these data points are not independent because they come from the same state. So that's what we call multi-level data, because we have different levels of variation. We have the overall, individual level variation, and then we have state level variation as well. We have 2 levels where there can be variation in the data. Some people call it nested. And it's also kind of a repeated measures data set, because we have the same state was measured repeatedly over time. So what do we do about that? Well, usually we do what's called a mixed model. I'm not going to get into the technical specifics of that too much right now, but basically that's a type of statistical model that allows you to estimate the non-independence of data that come from the same subject, such as measuring multiple plots in the same block of a study, or measuring the same mouse every day on, measuring its body weight or whatever. Those are all non-independent, just like we're measuring the same state many times. And when you do a mixed model, you may have heard the term random intercept model and random slope model. Random effects is what we call it when we assign non-independence. We say that data are correlated because they come from the same state, or from the same person, or from the same plot or mouse, or whatever it is. And random intercept means we're saying that the baseline yield can vary by state, but we're gonna, in this particular model, we're not gonna say the slope can be different by state. We're just gonna say, instead of modeling one line for all the states, we're gonna model, like, maybe here's a state with low yield, here's a state with high yield, but we're modeling it as all having the same slope, just one slope. The states can have different intercepts, but they have the same slope. You could do random slopes as well and let all the states have their own trend, intercept, and slope. But we're not going to do that here for now, especially because if you go back and look at the data, I mean, they're quite similar. So it doesn't really seem like you'd need to, the slope is very similar in all those. So it doesn't really seem like we learned much from doing a random slope model. I mean, the intercepts aren't too far apart either, but just from looking at it, we could say that. Now, how do we do that in R? Well, a simple way to do it is through the function LMER, linear mixed effects regression. It's called mixed because it has a mixture of fixed effects, the effect that's constant across all the states, which is the slope by year, and it has random effects. The intercepts for each state come from a random distribution, so they're called random effects. So it looks a lot like our LM function, right? We had yield by year, data equals Southeast soybeans. The only difference is this plus part, this part of it. This is the random part of the model formula. And it says, what are the model terms that are going to be estimated for each of these groups? One indicates that it's going to be the intercept. And which are the groups? Well, it's the column state in the data indicates what group each data point belongs to. So the data are going to be modeled as having a different intercept for each state. LMER is the function. That's the only difference of what between what we had before. So we have to do year is the slope effect that we're estimating, and then we have to put parentheses around it. One showing it's going to be an intercept, for each state. And then we use this vertical pipe to split up the left and right side of that. And state is the group that we're grouping by. That means, okay, we're going to model yield as having a trend over time by year. And we're going to say each state can have a different intercept, but every time the same slope. I'll show a figure of that in a minute so you can see what it looks like. We're going to call that LMM for linear mixed model. Okay, everybody with me on this? And now we can also do our diagnostic plots for this one as well by doing check model. And we see similar situation of basically linear. Again, the variance isn't perfect, but that's not too bad of a deviation for us. It's going up, but not by much, and it looks normal as well. So we're good there. And now we can look at the summary of this. I'll look into this. So yeah, we have, yes, the summary looks a little bit similar to the linear model summary, but it has some extra stuff in it. First of all, yeah, you can see here's the overall intercept and here's the slope. It's actually not that different. It's still about 0.28. Yes.
Mine has error in initial.
It's probably a typo in your code. I can look and see. Go back over. Okay, so that looks right. So what happened? Not provided by package matrix. So yes, that could be. I think you're doing this on your own, right? You could try to reinstall the package matrix and see if that fixes it. Because it looks like something is missing from that package. So if you try to reinstall that, you may have to restart R before you do, because if you install package that is being used right now, it will, yeah, sorry about that. Yes. Let me try it. So then go ahead and you can view in the console that install install.packages parentheses and put in quotes matrix capital N. Okay. Let's try to install LMU4 again instead of matrix. Try that. Oh, yeah?
Yeah.
And what was that? What version of R? Yeah, okay. Well, let's see about. Let's see if it works. Just highlight everything. Okay. Now, yeah, I guess that was Now let me what version of R? Go all the way back up to the top of this console thing. Yeah, scroll all the way up. Yeah, I mean that's like pretty new version, so that's weird.
Well, I can try to help you with that in a bit. We can move things forward, but it's not sure what's going on, but we'll figure it out. Sorry to not be able to fix it real quick, but
Okay, so yeah, let's see. Yeah, I mean, I guess you could try updating R as well. That would be a decent way to try. Yes, we noticed it didn't actually change the overall estimate of the slope that much, but it did give us the variance of the intercept between states. So there's, yes, the intercepts of the different states have a standard deviation of 2. So there's a decent amount of variation our model is telling us in the kind of baseline yield of each state, even though they were modeling them as having the same trend over time, if that makes sense. And we can also do a ANOVA on that as well. We get a similar result. And what was this that I was having y'all do? Yes, you can use the coef function if you want to look at the actual estimates of intercept and slope for each state individually that the model, if you wanted to know the specific state level predictions of the model, you could use coefficients to get that. And that tells us, yes, so we've modeled, yes, you can see that the slopes are exactly the same because we forced our model to estimate the exact same slope for every state, so they're the same. The intercept, again, it's like the yield at year 0, which makes no sense, but you can see that they're a decent amount different between the states. They're different by somewhat. So there's a slightly different interpretation of this model versus the one from before, and it correctly accounts for the ones from each state not being independent. So we should use this model over the other one. And yeah, the last thing I have in lesson 1, this is I don't really need you to worry too much about the code since I don't really want to teach you this code right now, but I just wanted to show you how you can make a graph of the model predictions to show you what those lines look like. Basically, just to keep it brief, I've created a prediction for the linear model from the linear mix model for each state so that I can make a line and show the predictions. And I've done it by state, and I've also done it by overall, setting the random effects to 0 so we can get an overall prediction as well. That's what this code is doing, and then make a plot of it. In this slide, I said I have no idea how to make this plot with SAS. Since I wrote that, I think I figured it out. So I put the SAS code to make a similar plot in the SAS code that accompanies this lesson as well. So you can look at that if you're into making graphs with SAS, which isn't much fun because SAS doesn't make very good graphs. But yeah, just to show you this, just kind of as a proof of concept, this is what this linear mixed model was doing. You can see the black line is the overall trend, and we've allowed the intercepts to be different between the different states, but same slope. So this is like the overall prediction, that black line, and then the states are allowed to have different intercepts. So it looks like South Carolina is at the bottom in terms of its baseline yield. And what's at the top? I guess Florida or something, I think. Anyway, that is lesson 1 of the R for SAS users curriculum. So give yourselves a pat on the back for making it this far. Yeah, and to just sum up, we've kind of gone through some of the steps of what you do with a very artificially simple data set of importing it, doing some exploration on it, and making a statistical model.